So good morning, students. Yesterday we have discussed about the thick cylinders and the basic formulas that are required to calculate the stresses on the circular disc or circular materials. Okay, so we'll discuss that in detail today. So for a plane stress, so the thick wall cylinder subjected to internal and external pressure. Subjected to internal and external pressures. So for the for these type of thick cylinders, we have to find out the state of stresses. So this you can take as radius r, and from the center O, and there are two pressures, that is the internal pressure that will be there from inside this material due to any reason, and we'll name that one as Pi because it is internal pressure Pi, and external pressure like this. So we'll name this one as P naught or P, whatever it is you can name. This is the internal pressure and the external pressure. If I draw the cross section of this one, it is going to look like this, right? Thickness, this one and this. So this is all internal pressures Pi and external pressure P naught. Okay, so if I take this as internal distance A and this distance from the center as B to find out the state of stresses. So I am naming that internal radius to the internal fiber, it is A, and external radius to the extreme fiber of the material, it is taken as B. So for this case, the formula have been derived, and it is the sigma r equals to A square internal pressure Pi minus P square P naught divided by B square minus A square minus Pi minus P naught A square B square divided by B square minus A square into R square. And sigma theta equals to A square Pi minus B square P naught by B square minus A square plus Pi minus P naught into A square B square by B square minus A square into R square. So these are the stresses that are calculated. There is sigma r and sigma theta. And for this, if you substitute the internal and external pressures, you will get the, it depends upon the cases. Like if I take case 1, that is a cylinder subjected to internal pressure only. Subjected to internal pressure only. So when it is subjected to internal pressure only, that is internal subjected to internal pressure only. That is P naught equals to 0 and Pi equals to P. That is internal pressure. Some internal pressure is there. So if you substitute these values, you will get sigma R equals to. So this term will be 0. This P naught term will be 0 in this equation over here, because P naught is 0. And if you, here also P naught equals to 0, if you substitute those values in these equations to 0, then you will get the final state of stresses, that is P into A square by B square minus A square into 1 minus B square by R square. Okay, and similarly sigma theta equals to P into A square by B square minus A square to 1 plus B square by R square. Okay, so these are the two general equations, and this is when the case of the internal pressure is 0. That is sorry, the external pressure is 0. Okay. If the internal pressure is 0, then the formula can be changed. And in this case, you can also draw the stress diagram if you want how it is going to look. That is, there is internal pressure and there is no external pressure. So the stress diagram for this is going to be like this. So this P naught equals to 0, and the stress at this fiber, extreme fiber, the stress at this extreme fiber will be 0, and there will be some stress internally at this fiber, at this junction, and slowly it will reduce down and it will come like this. This is sigma theta, and sigma R along the radial direction. The stress at the internal pressure will be there, and external it will be 0. At this point it is 0. So this is sigma R, and at this particular point it is P. So this stress diagram is in the case for internal pressure is there and external pressure is 0. So in the case of the second case, that is the external pressure is not equal to 0 and internal pressure is 0. That is, if it is case 2, Pi equals to 0 and P naught equals to P. In that case, if you substitute the values in the basic equation 1, then sigma R equals to minus P into B square divided by B square minus A square, and 1 minus A square by R square, and sigma theta equals to minus P into B square by B square minus A square into 1 plus A square by R square. Okay, this is the formula for the when internal pressure is 0 and external pressure not equal to 0. So the basic formula is this one which will be useful for you to remember, so that you can apply when for the given problem if there is an internal pressure or external pressure. Based on that you can substitute the values over here and get the solution. So that is the general equation that we have derived for the these kind of circular materials. So in the case of rotating disc, so the next type of problem is that is the rotating disc of uniform thickness. Uniform thickness. So for this one, what is the state of stresses, that is sigma r and sigma theta, which are given as sigma r equals to c plus c1, which are the constants, 1 by r minus 3 plus Poisson's ratio mu by 8 into rho into w square into r square. So this rho into w square into r square is the external force, that is the centrifugal force. So we have in basic in 10th class and the lower at the intermediate level, you have discussed what is centrifugal force and centripetal force. So the centrifugal force is something that acts away from the direction, and the centripetal force is something that acts inwards. Okay, so that is the external force. We also know that the equilibrium of this circular disc is, we have already derived that. So let me write that side of here. That is dou by sigma r by dou r plus, this is the equation that we have already, basic equation that we have already derived it in the first class of polar coordinate system. Sigma r minus sigma theta by r plus fr equals to 0. Okay, fr equals to 0. Right. So this is the general equation, and from this fr is the centrifugal force. That is what I'm saying. The force that is acting away from the particular rotating disk is called the centrifugal force. So that force is nothing but rho into omega square into r. Okay. So later on, if you simplify that, you are going to get you are going to get this equation for sigma r and sigma theta. You are going to get c minus c1 into. So don't worry about these c and c1. They are the constants which can be found out later on. Or in the problem, based on the problem, we'll substitute those values. Minus 1 plus 3 into Poisson's ratio divided by 8 to rho into omega square r square. So these are the general equations for the rotating disk. So for this case, the stress values are these. Okay, so there is a derivation for this one. It might come for the exam also. If it is a theory exam, it might come. If it is a it is online exam or a bits in a bits format, then they might ask you to solve the problem for this one, or they might ask you to write the general basic equation or identify the correct answer, something like that. So they will give something related to this derivation also somewhere in between you can get any kind of equation. So this is for the case of rotating disk of uniform thickness. So the derivation is there in the material which I'm going to share uh, with you. Then the next case is the solid disk. That is the solid disk. That is the okay. So for this case, the stress values are for the case of a solid disk is sigma r equals to 3 plus Poisson's ratio by 8 into rho into omega square b square minus r square. Then sigma theta equals to, for this case, is 3 plus Poisson's ratio divided by 8 to rho into omega square into b square minus 1 plus 3 Poisson's ratio divided by 8 into rho into omega square r square. So in this particular case, for a solid disk, it is required to take the constant, that is the constant which I was talking about, C and C1. C1 should be taken to 0. Otherwise, the stresses at the stresses sigma r and sigma theta becomes infinite at the center. The constant C is determined from the condition of the periphery, that is the boundary condition. You can get the constant C value. Okay, so in this case, you can calculate the state of stresses for a circular disk using these formulas sigma r and sigma theta. So in this case, when the internal that is r equals to 0, then when r equals to 0, sigma r and this term will become 0, because you have r over here. If it is 0, then automatically it will become 0. Then sigma r and sigma theta will be 3 plus Poisson's ratio divided by 8 into rho into omega square into b square in the case of r equals to 0. So this is a solid disk. There is no hole in between. That is in this format, there is no hole at the center. So r will be internal radius. Internal radius will not be there. If you take that one to 0, then the sigma r and sigma theta are equals to 3 by Poisson's ratio, 3 plus Poisson's ratio divided by 8 into rho into omega square into b square, where b is the distance from the center to the outer fiber. So this is this is in the case of rotating disk. So for this also there is a small derivative which is there in the material, which you can see later on. Then comes the circular disk with a hole. Then comes the next type of cases. Circular disk with a hole. So this is a case where the material, there's a hole at the center, and for this, if you use the want to find out the state of stresses, then they are given as sigma r equals to 3 plus Poisson's ratio divided by 8. into rho into omega square, and b square plus a square minus a square b square by r square minus r square, and sigma theta equals to 3 plus Poisson's ratio divided by 8 to rho into omega square to b square plus a square plus a square b square by r square minus 1 plus 3 Poisson's ratio, 3 plus Poisson's ratio to r square. Okay, so these are the two types of stresses that which we have to identify. This is the formula, and the derivation for this is quite tedious. It is going to take more time. How to find out these sigma r and sigma theta. So I've given you directly the formulas which will be useful for you to solve the problems if it is coming from this particular topic. So this is the finally whatever we are finding out is only to find out the state of stresses along the circumferential direction and the radial direction. Okay. So I will share you. So we have discussed these different types of stresses for different cases. That is for a solid disk, for circular disk with a hole, and we have discussed about the rotating disk of uniform thickness. So really, will these equations or these whatever formulas which I am sharing will be used in the real life? Will they really use this to find out the state of stresses for these materials? Is one question. So I would like to share one small video where they have how they have used these stresses, and how based on these stresses they can, if they know the state of stresses, then they can take a decision whether to increase the size of the materials or to reduce the size of the materials, or the thickness can be reduced or what. So I will show you one small video where what happened in that case where the material has failed and how they have plotted the stress relations, so that you will understand, yes, these really are useful or not is what you can decide.
On July 19, 1989, experienced a catastrophic failure of the turbine disc in the tail engine, which severed the hydraulic control lines. Failure of the disc in the tail engine was driven by dynamic loading that propagated from a defect in the original casting of the disc.
United 232 Heavy Sioux City. We have no hydraulic fluid, which means we have no elevator control. Almost none. Like in the airport. If you've got someplace near there that we might be able to ditch, and let's get control of this airplane, we're going to put it down wherever it happens to be. United 232 Heavy, roger, stand by one.
The inertial forces of rotation can cause the disc to tear itself apart. The equations that are used to determine the hoop or tangential and radial stresses are given right here in equation 355. You will notice that in order to calculate these stresses, we need to know the angular velocity of the spinning disc in radians per second, the density of that disc, I actually prefer kilograms per cubic meters, the Poisson's ratio of the disc material, the inner radius, the outer radius, and the position coordinate r as we move from inside to the outside outside of the disk. Now keep in mind that these equations only apply for true thin disks, where the thickness of the disk is small compared to the outer radius. If we take those equations and enter them into a spreadsheet, we begin at the inner radius. I always do increments of 100. So I take the distance between the inner and outer radius, divide it by 100, and I add those little increments to move from, in this case, 2 centimeter inner radius to a 30 centimeter outer radius. I plot the tangential stress using this equation here and the radial stress using this equation here. And we look at the sensibility of these answers to get a notion of whether or not we've got the equations right. As this disk spins, it's trying to tear itself apart. So our hoop and our radial stresses are going to be tensile. The radial stress, of course, since it points in the direction of the radius, has to be 0 at the free inner radius right there, and it has to fall back to 0 at the outer radius. Well, a plot of the tangential and radial stress, tangential stress shown in blue here, radial stress starts at 0, rises and drops to 0 at the outer boundary. You'll notice that the highest stress is in the hoop direction and at the inner boundary of the rotating disk. I mean, this makes sense. And so the more mass you have rotating trying to pull away, the higher the stresses will be. So in this case, I have my density in kilograms per cubic meter. I initially input the angular speed in RPM, but I convert it to radians per second. I have inner and outer radius in centimeters, but you have to convert all of these distances to meters when you do the calculations in equations 355. You also need to know the Poisson's ratio of the material in order to do this calculation. So the nice thing about all of these sorts of problems when you build a spreadsheet is you can see the effect of angular speed. Let's just say it's RPMs. If we lower the angular speed, we are going to lower the stresses. If we increase the angular speed, we are going to increase the stresses. In fact, as R goes to 0, you encounter a singularity. So if you want to include the possibility of a solid circular disk that is spinning, you have to modify these equations by letting the inner radius go to 0 and eliminate the first and third terms in both of these equations. Then you can plot it for a solid disk that has no opening. Now, I don't usually do that because all of the rotating structures that we ever look at are attached to a shaft, and so they have a hole, an inner radius hole in that disk. So this is the way you would build a spreadsheet. Pretty straightforward thing to do. This is one of your assignments for Sunday.
So as you can see from that live example, how he has interpolated the failure of the particular material based on the diameters and the thicknesses, the shaft based on the shaft diameter internally, the material had failed somewhere in between, and it is a small part in the aeroplane which you have seen in that video. So that is how it is going to be there. In reality, yes, these formulas, these discs will be coming everywhere in the everywhere in engineering field. Then wherever it is required, you have to apply these concepts. So for coming to the civil engineering, you might ask where it will be useful. Yes, in the civil engineering also, definitely it will be useful to useful in the case of water tanks when you design a circular water tank. And when you can apply the pressures internally, the water pressures, and because of those internal pressures, what is the variation of the stresses along the thickness of the wall or the water tank. So in different cases, there will be many cases where you can use this, find out these stresses for different types of conditions. Like it is a solid disk or when it is a rotating disk or when it is a circular disk. Okay, so that's all for now today. So we have completed that. We have time. So if you have anything to ask or anything, I'm ready to answer if you have any doubts in between anywhere. So this is the rotating disk with uniform thickness. The equation of equilibrium which we found out, that is dou into sigma r by dou r plus sigma r minus sigma theta by r plus Fr equal to 0, where Fr is the external force, which I was saying, and this Fr is nothing but the force per unit volume, and it is nothing but the centrifugal force rho into omega square into r. If you substitute that and simplify this equation, the equilibrium equation, then you are going to get and all the values if you substitute in between, you are going to get this final state of stress sigma r and sigma theta. But before that, you can see this expression over here, r square, the first expression, r square into dou square y by dou r square plus r into dou y by dou r minus y. So it is in the form of an equation of degree 2. So for this degree 2, we have in calculator also. If it is a problem, we can solve it, but this is not a problem. We have to go in depth in calculation. So here, simplifying this equation will give you this y equals to y value equals to cr plus c1 into 1 by r minus 3 plus Poisson's ratio by 8 into rho into omega square r cube. So that is the solution. That is the solution for the above differential equation. So the above one is the differential equation. That differential equation, the solution for that is y equals to this particular equation. So using this y equals to this, if you substitute in from equation 6.41, which is given over here at the top, 4.1 and 6.42, if you use them, then you will get the final state of stresses, that is sigma r and sigma theta. So anyhow, I'm going to share this material with you, so you can go in detail how they have calculated this. And then the solid disk, the same thing. So here in the solid disk, you are extending it from the rotating disk to the solid disk, where C1 should be taken as 0 at the center, otherwise the stresses will be becoming finite at the center. So for that case, for the solid disk, sigma r and sigma theta are given over here, 3 plus Poisson's ratio divided by 8 into this one. And if r equals to 0, that is the internal pressure is equals to 0, you're going to get r sigma r and sigma theta equals to this particular value. Then a circular disk with a hole, with this a hole in central. So this is the formula where sigma r and sigma. So these formulas are similar to the video which I have shared. In that video also, you can see that sigma r and sigma theta are equals to 3 plus Poisson's ratio by 8 into rho into omega square. So omega is the angular frequency. So at what speed it is rotating, the disk is rotating at what speed, and depending upon that speed only the stresses will change radially and circumferentially. Okay, so here these are similar to the formulas which I have shared, and they can identify the stresses and the material, and based on that they can design the material. Okay, so that is what I have discussed for today. So I will share this material. You can go through it further, and if there are any problems, I am going to do it, and you can also solve it if there are any problems related to these different conditions. And for your like this is like a exam which is in the form of bits. So for that, this class will be useful for you. If it is a theory, and if you have to come and write for 3 hours, then there might be derivatives required. But however, irrespective of the exams, it is very interesting for you to understand and study the derivatives also, how they have found the stress formulas and the along the radial and circumferential direction. Okay. So I will share, as one of the students is asking about the yesterday's problem, I would like to share with you those problems. So that you can see this one. So thick cylinder with pipe of outer diameter 300 mm and thickness of the metal is 50 mm is subjected to an internal fluid pressure of 40 MPa and external pressure of 2.5. Determine the maximum minimum intensities of circumferential and radial stresses in the pipe section. Plot the stress variation across the pipe section. So this is what you were asking, right?
Yes, sir.
Yeah, you want me to play this video?